Hi, and welcome to 11.2 Resistance and Resistivity. In this video, we continue our talk of electricity, and we're going to talk about resistance in a wire. As we go on, we're going to talk about circuits, and in those circuits, you could have different elements. You'll probably have a battery, maybe a light bulb or two, and everything's going to be connected with wires in at least one loop. So we call this a simple series circuit, and when it's all connected, the light bulbs turn on and there's current running through the wire. So we learned in class that current goes out of positive and into negative, and we drew some better circuit diagrams than this. But for this video, we're not going to really talk about the voltage supplied or how these things are connected, if they're in series or parallel. We're going to talk about what affects the flow of electrons in the circuit. Basically, how much resistance is being felt. And the thing is, the more things that are in your circuit, the more resistance there's going to be. It's kind of like adding sticks to the river. We could look at the water analogy like we did in 11.1. So basically, the more light bulbs or the more things we have in our circuit, the more resistance there's going to be. And we could think of the water flowing, and if we add a light bulb, it's like a stick in the river. Beaver comes along, adds another light bulb, there's another stick. The more sticks in the river, the less flow of electrons there's going to be, the less flow of water. So we're looking at this analogy and we're saying, okay, the more resistance, the less electron flow there's going to be. Well, what about this? Sure, we could add things to the circuit, but let's look at just the circuit itself. It's made of wire. There's wire connecting everything. Does this wire right here, does this have any play in the flow of electrons? What if the wire was made of a different material? Would it conduct electricity better? Would it be easier to flow through? What if the wire was a different shape? What if it was a thicker wire? Or what if we use more wire? What if the wire was longer? So there's basically 3 things that we can change about the wire. So in this video, we're talking about the wire itself, not really anything connected to it. So here are the things that we are going to change about the wire. So resistance in a wire. What can we change to change the resistance of the wire? We could change the material, or we could change the shape of the wire itself. So if we think of a wire as just a long tube of metal, basically a cylinder, what are 2 things we could change about the cylinder? Well, we could make the cylinder longer, like that, and we could also make the cylinder wider, something like that. But as you'll see in our formula, we don't really talk about the width of the wire. It's not really the diameter that we're taking into account. It's what they call the cross-sectional area, and we discussed this briefly in the previous video. If you cut the wire at a certain point, and you look at it from this view right here, it looks like a circle, right? Because it's a cylinder. So what's the area of that circle? Otherwise known as the cross-sectional area, because a cross-section is just that. It's like when you cut the thing in half. So if we cut it here, you get what's called a cross-section. So what's the area of that cross-section? And it's always going to be a circle. So those are the things that affect the resistance of a wire. Let's come up with a formula that relates them. So what happens to the resistance if we increase the length? And in class we said, well, if the wire is longer, the longer it is, the more stuff is in the way. So it's like adding more and more sticks to the river. So the longer the wire, the more resistance, and that's a direct relationship. So we'll put an L in our numerator. Hint, there's going to be something in the denominator. But basically, it's a direct relationship. The more length, the more resistance. So definitely going to be in the numerator. Now let's think about the cross-sectional area. If we have a wire that's thin and a wire that's thick, which one will have more resistance? In other words, which one will slow down the current more? Or we could think of which one has less resistance, which one will allow more current to flow through. And now the water analogy isn't really a river anymore. Let's think of it in terms of like a hose. Which hose will allow more water to go through? Hopefully you think that this hose allows more water to go through because the opening is bigger. It allows more water flow. So the thicker the wire, the more current. So this has more current. The river is flowing fast. With our thick wire, there's more current here. So that means that there must be less resistance. So there's more current because there's less resistance. And what type of relationship is this? It's not direct. Direct is more. Inverse is more. The more of something, the less you get. So the cross-sectional area, which we'll just use an A, is going to go in the denominator. If this goes up, this goes down. But remember, the current also goes up. There's more current, less resistance. We'll get into this more when we do Ohm's law and the relationship between resistance and current. Hopefully that makes sense, because now we're going to do something with a Greek letter in it. We have one more thing that we have to talk about, and that's material. What type of wire is this? Is it copper, silver, aluminum? You could technically make a wire out of any type of metal. So how are we going to assign a number to the materials? It's easy to assign a number to length. You just measure the length of the wire in meters. And we could calculate the area of the wire in like meters squared. But what is this material? How do we assign a number to aluminum or a number to copper? How do you assign a number to a material? We've seen something like this before, actually. Let's look at our reference table. We've had to deal with assigning numbers to different types of materials before when we did friction. So when we did friction, if it was rubber on concrete, how do you assign a number to rubber on concrete? Luckily, there's these coefficients of friction that we used, and we also used a Greek letter, mu. Now we're going to go to our electricity page where we can see all our formulas, including this one that we're going to finish making. We're almost there, but we need, what is this? Is that a P? No, it's not a P. It's a Greek letter for something called weird. It's called resistivity. Resistivity is how we we assign a number to a material. So luckily, we don't have to like try to make our own numbers. They give you a lot of numbers to plug in. If the problem says it's a copper wire, you'd plug in 1.72 times 10 to the negative 8 for rho, which is the letter that we use to represent the resistivity of the wire. It's basically like how readily does this material allow electrons to flow through it. So the higher the resistivity, the more resistance there is. So which one of these numbers has the highest resistance? Might be hard to see, but it's actually nichrome, because it's 150. It's not really in scientific notation correctly. The decimal points over here, all these other decimal points are where they should be. So as you can see, they use nichrome for anytime you want a super high resistance in the wire. And copper is typically what we use in wiring in our house. It has a relatively low resistance. So more flow is going to flow through this, more current. So this is how we assign numbers. This is resistivity is a rho. It's a Greek letter. And the more resistivity, the higher this number, the higher the resistance. So this has a very high resistance because it has a high resistivity, nichrome. And copper has a lower resistance than nichrome does because the resistivity is lower. It's just kind of like an intrinsic property of that material. So what type of relationship is this? They do the same thing, so it's direct. And we're going to plug it in here. If you look at the units, they're in ohm meters, and resistance is measured in ohms. So we have, this is ohm meters, ohm times a meter, and length is measured in meters, and the area is measured in meters squared. So why is it ohm times meters for the resistivity? Because when you do an ohm meter times a meter, you get ohm meter squared. And an ohm meter squared divided by a meter squared cancels out, leaving you with ohms for resistance. Okay, 10 minutes in, we're ready to do the homework. You could have just read this probably. Anyway, number 1. A copper wire of length L and a cross-sectional area A has a resistance of R. A second copper wire, so it's the same material, same resistivity, at the same temperature. Oh, we didn't really talk about temperature. It's not in this equation because the resistivity is given to you on your reference table, and all of these values are assuming resistivities at 20 degrees Celsius. So that kind of takes care of the temperature for our equation, but it's good to know that temperature is also directly related to the resistance, or at least approximately. If the wire is hotter, that's going to lead to an increase of resistance. So let's go back to the problem. The second copper wire is at the same temperature and has a length that's different. The length is half L and a cross-sectional area of 1/4 A. What is the resistance of the second copper wire? This looks like a relationship problem to me. So once I know what I'm changing and what they're looking for, I try to find an equation that relates them, which is the one we just made. And then I plug in the numbers that they want me to plug in. It's 1/2 L and 1/4 A. But I can't just start plugging numbers on one side and expect this to still be equal. I have to, whatever I do to one side, I have to do to the other. So I put a 1/2 in the numerator here and a 1/4 in the denominator. And we have a really ugly improper fraction. So we have to change the division to multiplication and flip that to 4/1. And then you multiply the numerator. 1 times 4 is 4. Multiply the denominator. 2 times 1 is 2. And 4 divided by 2 is 2. So you get double the resistance if you decrease the length by half, but you also decrease the cross-sectional area by 1/4. So it's going to be choice B. Number 2 is pretty similar. It says, which changes would cause the greatest increase in the rate of flow of charge through the conducting wire? So it's increasing the rate of flow of charge. We want more current, which we said before, if you have more current, that means the electrons are flowing easier. And if they're flowing through the circuit easier, that means there's less resistance. So the first thing we had to look at is what exactly do they want us to do? Do they want more resistance or less resistance? Since it's increasing the flow of charge, that means that there's less resistance in the circuit. So which one of these would cause R to decrease? And we're going to do the same process as number 1 and plug in some numbers, or let's use arrows. If you decrease the surface area of the wire and decrease the length of the wire, well, first of all, I guess by surface area, they mean that cross-sectional area that we were talking about before. The problem really should say cross-sectional area to make it more clear. So let's see. How would we get the least amount of resistance? Well, if we decrease the length, then we're going to decrease the resistance because that's a direct relationship. But since the cross-sectional area is actually an inverse relationship, if we wanted the resistance to decrease, the area should increase, and that'll cause even more of a decrease. So it says the greatest change, then we would want both of these things. We want a smaller length and a greater area. So that's going to be choice C. You increase the area, greater area, and you decrease the length, smaller length. Okay, so now we have at 20 degrees Celsius. So this is a clue. 20 degrees Celsius tells us we might have to look at our reference table because they're specifying 20 degrees, and that's really the only place you see 20 degrees on the reference table. So at 20 degrees, 4 conducting wires made of different materials have the same length and the same diameter. So which wire has the least resistance? So now the length and the area are the same. We're just changing the resistivity or the material, which would have the least resistance. We're looking for the smallest resistivity out of copper, silver, nichrome, and tungsten. And here we have copper, silver, nichrome, and tungsten. Which one of these has the smallest resistivity? It's going to be silver. Silver is 1.59, and that's only 1.72 copper. And remember, this is 150, not 1.50. So this is 1.59. This is big. This is 150. So don't get tricked into that. And you might think to yourself, wow, silver's less resistivity than copper? That's really efficient. Why don't we wire our houses with silver wire instead of copper wire? Well, because that would be super expensive. But silver does have the smallest resistivity, which brings us to the smallest resistance out of those four. Number 4, a copper wire has a resistance of 300 ohms. What is the resistance of a second copper wire with 3 times the cross-sectional area and double the length? It's another relationship problem, so we write our equation and we plug in the numbers. It's 3 times the cross-sectional area and double the length. So I put a 2 in the numerator and a 3 in the denominator. So it's going to be 2/3 of the original resistance, which was 300. So it's 2/3 of 300. So that's going to be 600 divided by 3, or 200 ohms. 2/3 is big. So now it says, what is the resistance at 20 degrees of a 3.5 meter length of nichrome wire with a cross-sectional area of 6.8 times 10 to the negative 7 meters squared. We could finally do one that's a straight up guess method. It says the length is 3.5 meters. The area is 6.8 times 10 to the negative 7 meters squared. And if you think about it, the reason it's such a tiny number is because it's the area of this tiny thing. It's like the thickness of the wire almost. And what else are they telling us? They're giving us a clue. Go look at the reference table for nichrome. What is the answer? For what is the resistivity we're looking for? 150 times 10 to the negative 8 ohm meters. Don't forget the units. They're right there for you. Don't forget to write the units. Also, the resistance is what we're looking for, so that's the unknown. We have our equation. We'll substitute in the numbers, and we will solve. And you get a resistance of 7.72 ohms. Okay, number 6. Number 6 says a 0.686 meter long wire has a cross-sectional area of 8.23 times 10 to the negative 6 square meters. And now they're telling you the resistance is 0.125 ohms. And they do specify, again, 20 degrees Celsius, which is a hint that we are going to look at the reference table eventually. But they don't tell you the material. It says determine what this wire is made of using the materials listed in the resistivity section of your reference table. So that's a big clue that we definitely have to look at our reference table. But we don't know what the material is. So we have to calculate it using our formula. Now at this point you could cross multiply and solve for rho to get a handy formula for the resistivity, because that's what they're looking for in this problem. Normally, though, to be consistent with what we've done in the past, I'll plug in the numbers and then solve. But I'll be honest, if I was solving for these, I typically solve for the variable first, which is a good way to do it, either way. So let's substitute in the values, cross multiply. So like this is over 1, it's this times 1, and then 0.125 times that number, which gives you like 1.03 times 10 to the negative 6. So we'll set that equal to 0.686 times rho, and then you divide by 0.686 to solve, and you get a resistivity of 1.4996 times 10 to the negative 8 ohm meters. Don't forget ohm meters, that's the unit for resistivity. Oh, wait, I transferred it over. It's -6. If you look at your reference table, These are all in terms of 10 to the negative 8. So we have an answer in terms of 10 to the negative 6. So to handle that, you just move the decimal place 2 places over to the right, and that'll give you 149.96 times 10 to the negative 8 ohm meters, which is basically 150. So it's nichrome, 150 times 10 to the negative 8. So this is nichrome. Number 7, a 10 meter length. Okay, so L is 10 meters of copper wire. So, and it's 20 degrees Celsius. They're giving you a hint. Look at the reference table for the resistivity. Copper is 1.72 times 10 to the negative 8 ohm meters. And they're telling you the radius of the wire. What a weird measurement to give. Who says the radius of the wire? 1.0 times 10 to the negative 3 meters. Okay, calculate the resistance of the wire. We're looking for the resistance. Well, we want to use this formula. We're looking for the resistance. They tell you the length. They tell you basically where you could find the resistivity. And we need a number to plug in for the area. They give you the radius. The radius is not the area, but we know our shapes. The shape of the cross-sectional area, as shown here, is a circle. So how can you find the area of a circle? You don't even have to memorize the formula for the area of a circle because it's in this handy section, the geometry and trigonometry section, which we hardly ever look at. But for circles, they tell you the area is equal to pi r squared, and they're telling you the radius. So this is a two-step problem. First, we have to use the radius to find the area. Don't forget to write the units for the radius to get full points, and that'll tell us what the area is so that we could plug it in our formula. So the area we plug in right there, which gives us a resistance of 0.05 ohms. And you could rewrite this as 5.5 times 10 to the negative 2 in scientific notation. Okay, number 8 says compute the resistance of an aluminum wire. So the resistivity is 2.82 times 10 to the negative 8 ohm meters. It's 2 meters long and 8 millimeters, or they're actually giving you the meters version of that, which is nice, 8 times 10 to the negative 3 in diameter. What a pain in the butt. At least it's more reasonable. Like if you were measuring the diameter of the wire, it's more reasonable than telling me the radius. So this is the diameter. We definitely want to find what the area is first. So pi r squared. And the radius is half of the diameter. So this would be 4 times 10 to the negative 3 meters. So you plug that in. Make sure you're super careful with, the scientific notation in the calculator. Parentheses are your friend here. And you get an area of 5.03 times 10 to the negative 5th meters squared. So that's the first step. Now we're ready to calculate the resistance. Plugging in. And you get 0.0011 ohms, but that's not how we write it. That's much better. All right, number 9. Probably the hardest one. Let's see. A length of copper wire and a 1 meter long silver wire have the same cross-sectional area and resistance at 20 degrees Celsius. What is the length of the copper wire? So we could write down the resistivities of each thing, and okay, the length of the silver wire is 1 meter, and you're looking for the length of the copper wire. I'm assuming you did that all already, do the guess method. I'll just show you the way to do it. It's kind of more of a puzzle type of thing. So it's the same resistance and the same area. And we're going to write our equation. But remember, we're dealing with the copper, so C for copper. and the silver. So some things are different, definitely the resistivity and definitely the length, but some things are the same because they tell you the resistance is the same and the cross-sectional area is the same. So since the resistance is the same, all right, these two values are the same, we could actually set these two equations equal to each other. And we also know the cross-sectional area is the same, so we don't have to use different subscripts in this fancy equation that we made over here. It's the same thing. So now we can solve. You could either cross multiply or divide everything by A on both sides, or multiply. Maybe it's easiest to say, maybe let's multiply both sides by A. So whatever you do to one side, you do to the other. And A divided by A cancels out. That's fancy. That's sneaky because it's the same area. They tell you that in the problem, same cross-sectional area. So we're basically canceling out the areas. Now our equation looks like this, and they tell us it's a 1 meter long silver wire. So we know this number. We can solve for this number, or not solve, but we could look it up in our reference table, and now we could solve for the length of the copper wire. But let's get a little fancy and do that before. Let's not plug in any numbers yet. Let's divide by the resistivity of the copper. And now we have a fancy formula for the length of the copper wire for this particular problem. And while we're talking about this particular problem, the length is 1 meter. So if you substitute in 1 meter here, it's just the resistivity times 1. So the length goes away too. And now we have this formula, and we could look up the resistivity of silver and copper. Silver's here, copper's here. So you plug those in, and then you solve for the length. And you get 0.92 meters. So all said and done, it's not that bad. And this was a Regents question. So what I feel like is sometimes the people making the Regents kind of get like the expert blind spot. And they're like, oh, well, you end up just dividing the two numbers that you find in your reference table. That's not hard. And they forget that it's actually some thinking that you need to do before you get there. And you want to know what they do it on purpose. They want to throw you a curveball to try to see if you can think critically. So sometimes you have to do some fancy footwork to improvise, adapt, and overcome. Anyway, have a great day.